So let me recap your question. You said, what happens if we get parts A and B for a hydrogen atom? Let's as an example. So we would have a hydrogen atom shooter. We would have uh, double slits and a screen. And so just to reiterate, the picture over here would be basically just two little spots opposite. And that's because the hydrogen atoms go straight through and land on the screen and there's no interference. So that would be the answer to part A. And then part B, and I think I'm going to give a more complete answer here. So first off, so the hydrogen atom, well, so, okay. So all matter has wave-like properties. So, and if you remember on the other side, I said that electrons, the wave-like properties are measurable, or which is another way of saying observable. So for hydrogen atoms, the wave-like properties are unobservable. Unobservable, unmeasurable, we will never see them. They have no relevance whatsoever to anything. Unobservable, unmeasurable, practically don't matter. And what you'll see is that in the next one, we're going to actually calculate the wavelength of an electron. And when we do that, what I'll do is I'll also calculate the wavelength of a hydrogen atom, and we'll see that it is like 1,000 times smaller and therefore doesn't matter. So sort of that's why the first thing we need to remember is that it only matters for electrons. And the second thing, and it's a great question, so so it is true that all matter has wave-like properties, but for hydrogen atoms, for protons, for helium atoms, for anything else, it doesn't matter. It's unmeasurable. It will never, so there's never a interference pattern. So I think that's the next layer of complication, but that is how you would answer. Let's see. So the question was, explain how the pattern you drew in A is related to the nature of the electron. So if we were to answer that question for the hydrogen atom, we could say all of these things. We could also say that the hydrogen atom acts only like a particle, because particle-like behavior is they go straight through and they land on the screen, and they have no observable, no measurable wave-like properties. So I think that's the complete answer for that. Michael, what do you think of that, or any thoughts or any questions about it?
That's good. I just wasn't sure like how would I word it. I didn't know that all matter has wave-like properties. From the video, I think in the lecture, maybe I didn't watch it well enough, but I was under the impression that only electrons have those type of properties. But I do remember the little eyeball saying that we can actually observe the electron, but not. I think they were doing something else. I can't remember. Was it some kind of balls? I can't remember.
Did you want to talk about the eyeball?
No,
Because that's a whole nother thing.
Yeah, no, I don't.
Okay.
No, it's fine. But no, thank you. This is fine.
Sure. Well, yeah, because what you need to know is that electrons have wave-like properties, that the wave-like probabilities are what's actually interfering to create the interference pattern. And that's why you can shoot one electron at a time and still have it interfere. So, yeah. So there, and again, this stuff gets, and my emphasis in this course is just on understanding that electrons exist as probabilities. If you add the eyeball, that's another layer of complexity that we don't have to know about. I'm happy to talk about it though, say in office hours. Um, and then the other thing you have to know is that no other particle that we see does it because it's too heavy, has too much mass. And we will see that the more mass something has, the smaller its wavelength, and that's what makes it unobservable. So, yeah, I mean, this